has a huge sediment flux to the ocean. And that's in part because it is the largest river by discharge as well, supplying about 20% of freshwater flux to the oceans. And so included in that drainage basin is also a major organic carbon repository. And so when you think of that major sediment flux coming from that rich, sediment-rich river, it's mobilizing a lot of carbon in there as well. And this landscape is changing really fast. The drainage basin is 7.5 million square kilometers. And it's changing a lot due to deforestation, land degradation, and climate change feedbacks, which some of which have been intensifying in recent decades. So then when we step back and look at the carbon cycle, we can begin to understand what important role the Amazon plays in that. So this is the most updated global carbon budget that I could find, and it includes in the arrows the anthropogenic perturbations in the carbon cycle in the last 12 or so years. And then the major reservoirs that have been accumulating carbon in different places, which you see here from the different arrows and the numbers. So we're all familiar with this flux, this perturbation probably. It's due to fossil fuel burning. And on average, it's been about 10 gigatons per year in the last 12 years. And then in the background, there's always been this land sink from uptake of carbon dioxide in the atmosphere into vegetation, and then eventually into permafrost and soils on longer time scales. And then rivers give the chance for that organic carbon stored in land to be mobilized into rivers. And so because of land use change and climate change related feedbacks, compared to pre-industrial times, rivers have been mobilizing a gigaton more organic carbon in soil reservoirs mainly per year. So the Amazon River Basin is there's so many sediments coming from there. It is a good opportunity to learn more about what happens to particles that are mobilized in rivers. And particular organic carbon that gets mobilized. So in rivers like the Amazon, it's really, I see it like a balance between transport and respiration when I think about what happens to particulate organic carbon in rivers. And I kind of think about this in between two extremes. So scenario A is one extreme. In scenario A, the transport term is really strong, meaning that whatever gets mobilized from land into rivers ends up being preserved and buried in the coastal ocean. And then scenario B, the other extreme, is much less gets buried compared to what's mobilized because of processes that are happening in between, like carbon dioxide evasion due to respiration or sediment storage in the floodplains in the river basin. And so in the end, less gets buried compared to what gets mobilized. So the Amazon River for decades has been considered closer to scenario B. And that's because there's been large quantities of sediments being stored, which a lot of the previous talks have mentioned and described. And also there's been substantial measurements of carbon dioxide evasion, presumably coming from remineralization in the river system. And so the overarching objective of this talk and all the different parts of the talk are to ask ourselves, does the source of organic carbon matter and affect its fate, affect that balance between whether that particular organic carbon will be transported and buried versus remineralized in transit. And so part one will be focusing on the main stem at Obidos mostly, as well as some tributaries, looking at the origins and sources of organic carbon mobilized there. Part two will be connecting that to fate by looking at what gets buried in the coastal sediments. And then part three will be more about engaging with communities and some of the more recent work that I've been doing since this. So especially for parts one and two, our ability to get at that question really depends on the tools that we have as organic geochemists. And I like to think that there's two extremes in in the ways that we can look at the composition of organic carbon. We can look at it in bulk, and we can look at specific biomolecules, and then we can measure specific parameters for both of those things, like nitrogen to carbon ratios, and what I'll be mentioning a lot in this talk, stable and radiocarbon isotopes. So I decided to very quickly review isotopes, although I'm sure everybody is quite familiar with them in this talk, but I just taught isotopes in my 2 classes that I'm teaching, so I figured I'll just put the slides here. So stable and radioactive carbon isotopes. So stable isotopes can be differentiated as such. So imagine carbon in 2 different carbon dioxide molecules, and one of the carbons has 1 more neutron, so that's carbon 13. So it's slightly more massive than carbon 12. It's a very small difference of 1 neutron, but it makes a big difference in terms of how that carbon dioxide molecule will behave in the environment. So what I mean is really in this process of photosynthesis, which is primarily how carbon gets from the atmosphere to land. And in photosynthesis, you can imagine a plant or an algae cell would prefer to take up the lighter carbon, the carbon 12, over the carbon 13. So this fractionation, this preference, we can measure, and we display it in this notation called delta 13C. And so that's how I'll be talking about it, presenting it in this talk. And the range in delta 13C values observed in organic matter nature is quite wide, from -40 to -10. And it's diagnostic of something about the source of organic carbon, because we can see how different sources of organic carbon, especially on land, can partition between plants and soils, marine algae, petrogenic organic carbon. So this is a good proxy for the source of organic carbon. And then the other isotope that we have that I'll be talking about is radiocarbon. So this has yet 1 more neutron, and this carbon isotope is radioactive. So at a very steady rate, like a clock, it will decay to a stabler nuclide, carbon or nitrogen 14, and at a very steady rate. So assuming that we know how much radiocarbon a sample and a chunk of organic matter starts with, we can measure how much is left today and back out the age of that sample. And so we express this as cap del 14C, or fraction modern. I'll be mostly using fraction modern in this talk. And it ranges from 0 to 1, 0 being a very old sample, 1 being a very young sample. So these 2 proxies, or these 2 measurements, stable carbon and radiocarbon, have been used a lot for decades in the Amazon River Basin to study the dynamics of organic carbon there. So this is a study that's almost a couple decades old, looking at the bulk isotope composition of carbon dioxide and dissolved organic carbon and suspended particulate organic carbon in the Amazon River basin. And what these authors saw was that the red values for carbon dioxide are quite different than the values, the isotope composition of DOC and POC. And so from that, they concluded that it's primarily the substrate for remineralization in the Amazon comes from primarily young, relatively fresh plant sources in the Amazon River Basin. So they suggested that there is selective preservation of POC and selective remineralization of POC in the Amazon, which has inspired, after all this time, the questions that we'll be dealing with in this talk and in this study as well. So we're expanding that. I guess my goal today is to expand that toolkit for geochemistry using this other method called Rant Oxidation, which is kind of in the middle in the spectrum of bulk to compound specific measurements. So in the Rant Oxidation technique, if you look at the left, we put our sample, like from the Amazon, like particles from the Amazon, in a furnace that we increase in temperature at a steady rate from room temperature to 1,000 degrees Celsius. And we slowly oxidize that sample through time and through the temperatures. And that the oxidation products come out at the bottom, and they're linked to a vacuum line. And then with that vacuum line, we can trap organic carbon that gets oxidized in different temperature intervals. And so that's an example I'm showing here of how we're trapping one sample, one fraction of organic carbon that's come out at specific temperatures. And in that gas, we can look at the isotope composition of that carbon pool that got mobilized, that got oxidized in that interval. So here are some examples of data that come from the Rant Oxidation analysis. These are called thermograms. They're graphs of evolved carbon dioxide concentration against temperature on the x-axis. And first on the left here is a thermogram you would get from culturing coccolithophores. And these are non-calcifying, so we don't have to worry about calcium carbonate in this thermogram. So that's very fresh organic matter from a petri dish, and then from a culture, and then not a petri dish. And then in the middle here on the right is a comparison to mesopelagic zone particulate organic carbon from about 80 meters in the water column in the Southern Ocean. And so you see the difference there between those two thermograms. And then in addition, like I said, because of the vacuum line, we can trap carbon in specific intervals that corresponding to specific pools of carbon in the thermogram, and use isotopes and measure the isotope composition of that carbon that oxidizes in those intervals. So that's what I'm plotting here on the left. And the height of the bar is the isotopic composition of the gas that got released in those temperature intervals. So how we look at thermograms today is kind of, when we think of thermal stability of carbon over the thermogram, we like to interpret it as some reflection of the intrinsic bond strength of the biomolecules that get oxidized in specific temperature intervals. So you can actually convert the temperature scale here to activation energy. And we think of thermograms as sums of infinitesimal organic carbon pools that are on a spectrum of activation energy due to the different bond strengths of the organic molecules in those different pools that get released in the process. So that's how we'll be looking at thermal stability today in the Amazon River particulate organic carbon. So really we can break down this overarching question into a few questions. How can we partition particulate organic carbon in the Amazon by its thermal stability? What's the link between thermal stability and then the fate of that organic carbon? And then a little bit less related to thermal stability, but what I'll do in the end is talk about how communities can shape such research questions also. So to start, now that we have thermal stability as a tool to look at, I will start by just looking at particulate organic carbon in the main stem. At Óbidos, a few of the previous talks have described Óbidos as the most downstream gauging station that is free from tidal influence in the Amazon River main stem. So that's for that reason we got our samples from there. And we collaborated with some other groups that had gotten measurements from Solimões and Madeira rivers and the Tapajós River for comparison. So yeah, so we visited the main stem in 2 periods at high water level. There was a previous talk that talked about how variable the water levels are. So this is another example of that. This is actually, I think, the Tapajós River basin. We were still around the Tapajós River and not at Óbidos yet. And you can tell from the watercolor, it's not very brown. And we were working, yeah, we couldn't have done this without José Mora in Santarém and a bunch of hardworking Brazilian students that worked together with us. They had their own research questions too, but they were also helping a lot with the sediment measurements, Miyuki, Poliana, Hargiles, and Gabby. And here's Jose on the right hugging our ADCP. We use an ADCP to get a cross section of water velocities at Óbidos, which I'm showing you on the left here. And the color map is the water velocities, which we integrated to get discharge at those 2 times that we went to Óbidos. So on the right is a hydrograph in 2014 when we went. And the circles are our measurements of discharge from the ADCP. Generally, discharge was not so different between the 2 times, but they were at 2 times on either side of the peak water discharge for the year. So in April, the water levels were rising, and in July, the water levels were falling. And we use a depth-specific sampler to get particulate organic carbon, or to get total suspended solids at specific depths and locations in the cross-section to show that. So that's what I'm showing in the circles here. And this is just what it looks like when we deploy the depth sampler with the lids open. We keep it horizontal in the river and lower it to the depth we're interested in. And then we use a bicycle pump, the pressure from the bicycle pump, to close the lids at our location and depth of interest. And then we lift it back up out of the water. And so here's a depth sampler that effectively deployed, and it's full of that brown colored river water that is very characteristic of the Amazon River main stem. This is at Obidos. And then we filtered the suspended solids with diameters larger than 0.22 microns. And here is a reconstruction on the right of suspended sediment concentration using a model for depth-related sorting of the sediments by concentration. So you can see that here, how there's much more sediment concentration in deeper depths than shallower in the cross-section on the right. And we integrated the product of water velocity and sediment concentration to calculate a flux of suspended solids per second in April and July. So in April it was 53,000 kilograms per second, and in July it was 48,000 kilograms per second. That was a sediment flux at Obidos going downstream. And then we also measured the particulate organic carbon concentration in the sediments too. Generally, they're about 1% organic carbon. And so we also were able to construct cross-sectional concentrations of particulate organic carbon in the main stem. Again, there was, as you would expect, there's depth-related sorting by depth of the particulate organic carbon concentration. And in April, it was 540 kilograms per second, and in July it was 370, which I don't think it's the right thing to do this, but if we do scale it to annual, annual fluxes, it's quite similar to previous. It's within range of previous estimates of particulate organic carbon fluxes from the Amazon River Basin. So despite this depth-related sorting in particulate organic carbon concentration, there was very little variation of Amazon River POC by depth or location in the cross-section. So here is plotted on the y-axis, the nitrogen to carbon ratio, on the x-axis, delta 13C of the bulk organic carbon collected at Obidos in April and July. So those are the circles. And there isn't much variation in the values here, relatively speaking. When we took 6 of those samples from the main stem and analyzed them with the Rant Oxidation method also to construct thermograms. And the thermograms are really similar to each other too, regardless of depth, regardless of season. And when we look at specific gas fractions, so remember in these thermograms, I'm plotting bars, I'm overlaying them with bars to convey the isotopic composition of gas, radiocarbon and stable isotopic composition of the gas released in specific intervals. And we tried, generally the intervals are quite similar, the temperature intervals across these different thermograms. And in general, what I'm showing you here for the 2 sets of 6 samples, the isotopic composition, even in specific gas fractions, is not very different sample to sample. So when we look at the values, the bulk values of these samples in this nitrogen to carbon against delta 13C space, it tells us that the river POC is primarily reflecting the signal of fresh vegetation or soil organic matter. It could be either one. We are quite sure it's not reflecting in situ primary production. That's more the signature of the Tapajos River POC we saw, which is the green triangle here. It's quite different, quite removed from Tapajos in this space here. But so it could be vegetation or soil organic matter. But then when we look at the thermograms again and the gas the isotope composition of the gas fractions. That's how the gas fractions plot out. So here is the fraction modern against delta 13C for the individual gas fractions from all the thermograms that we got from Ovidos. And the color is the temperature of oxidation. And you see that no matter what gas fraction we're looking at, they're not, the isotope composition for those gas fractions are not very close to modern. And so this tells us that primarily particulate organic carbon in the Amazon River main stem comes from soil organic matter sources. It's not really from fresh vegetation. That's not what is in the suspended sediments. The other thing that I wanted to show you here on the right is that there's this trend from at cooler temperatures, the oxidation is reflecting younger carbon-13 depleted organic matter pools. And at the higher temperatures, the oxidation in the Rant oxidation technique is releasing older soils or older organic matter that is more 13C enriched. So you have this trend where radiocarbon age, as age increases, the 13C enrichment increases. So that trend, we think, reflects the flushing of soils from different horizons in the floodplain, because that's kind of what we expect in a soil profile in the Amazon River Basin, where the younger soils at the top are more 13C depleted and the older soils further down are more 13C enriched. And we see a similar pattern when we look at other tributaries as well. When we look at the Solomons River POC upstream and the Tapajos River downstream, we see something similar. So here I'm plotting, I did the Rant oxidation analysis for those samples as well. So here I'm plotting all three tributaries that we looked at and the individual gas fractions that we separated in the Rant oxidation technique. The y-axis on the left is radiocarbon and the one on the right is delta 13C, and the activation energy is what is on the x-axis. And you see how generally you have the same trend towards the pools of organic matter with higher bond strength, therefore higher activation energy. They tend to be the older pools that are more 13C enriched. And I just want to, I guess, point out, I haven't spent too much time looking at this. This is a newer plot that I did, but the slopes are more similar than the intercepts is the main take-home message that I wanted to convey here. So perhaps even if each individual tributary is mobilizing different sources of soil organic matter, you have the same thing happening with the mixing of soils with different degradation histories in each tributary. So yeah, I thought it was interesting that the data from all three tributary, well, the main stem and the Solomons and Tapajos exhibit a similar pattern. So this recaps part one. I've hopefully showed you how thermal stability is one way to differentiate different soil organic matter pools that get mobilized into the Amazon River, and how it reflects soil organic matter with different degradation histories. And also just going back to the depth-specific sampling method that we used, perhaps, although depth-specific sampling is important for estimating POC flux accurately, it might not be so important for understanding POC composition if there isn't much sorting by depth. So that's just, I thought that was an interesting result as well that could maybe improve the efforts that we focus on in future sampling at Obidos. So the second part is now trying to connect those different thermal stability, those different organic matter pools that we saw in the main stem to fate, to their fate in the coastal sediments. So a lot of this work is really being pushed forward by these individuals, Brenna, Kirsten Vallée, Brad, Jose, who are doing a lot, linking all those Rant oxidation analyses that I just presented to the composition of sediments that get deposited in the Amazon mud banks. And so I'm going to present this hypothesis that they're working on And I really suggest that you contact them if you want to talk about their hypothesis more and the field work that they have planned, the very exciting field work they have coming up for them. So to start, we're going to look at things in fraction modern against delta 13C space again. And so here's a composition of bulk POC at Obidos that I was just talking about. And here is when you separate out the POC in different gas fractions from the Rant Oxidation, the RPO method. And then this is when you convert it to activation energy. So like I had just showed you, the young POC soil pools are associated with the lower activation energy organic matter pools. And then the older stuff is associated with higher activation energy pools. And now this is how they look compared to the isotopic signature of the marine end member on the upper right corner, which is what you would expect for Atlantic Ocean primary production derived organic carbon. And then in the middle here is the bulk composition of organic carbon collected from mud banks from 1997 off of French Guiana. And so you see, if you had to draw a mixing line between the marine end member and what comes from Obidos, the only way to reconstruct what we see in the mud banks is to assume that there's mixing of a relatively refractory organic matter pool relative to the bulk organic matter at Obidos. And it gets more complicated when you separate out the mud bank organic carbon pools by activation energy through the RPO method, but still you get the same conclusion that there must be some organic carbon, the pools with lower activation energy that get lost between Obidos and the mud banks along the coast of underneath the Amazon plume. And so this reiterates that hypothesis that I talked about earlier that's been circulating around for a long time, that there is selective degradation and therefore selective preservation of organic carbon between the main stem and Atlantic. But I'm really excited about Brenna, Kirsten, Brad, Jose Vallier's crews coming up, because they will have the chance to kind of make that connection finally and collect mud bank sediments and do a broad suite of RPO analyses on them. And there was a previous talk, I think by Chuck, who was talking about how the tidal section of the Amazon is vastly understudied compared to the main stem and the coastal mud bank sediments. So maybe by doing this comparison, these individuals will be able to fill in some of those gaps, especially maybe those gaps that exist in what happens in the tidal part of the Amazon River Basin. So that concludes part 2. And yeah, I want to conclude this section, I want to now look at all the thermograms that I showed you. So I started by showing you thermograms of primarily marine organic matter, very fresh cultured phytoplankton organic matter on the left, to mesopelagic organic matter that's still pretty young, and then Amazon organic matter, presumably coming from soils that is much older. And you see that there's a progression in the thermogram shape, almost with the degradation state of this organic carbon. And so we're beginning to make linkages. The RPO method is beginning to help us better connect thermal stability to the molecular diversity of organic carbon in samples and their degradation state, and therefore their fate in the environment. And I suggest you look at the recent contribution by Jordan Hemingway and his co-authors, who are beginning to make these connections in these thermograms. So just a broader picture of perhaps what this method has in store for us going forward as more people use it. So, okay, we have like a little over 10 minutes left, which is great. And I just wanted to spend the rest of this time to talk about engaging with communities. I think it's inevitable that we interact with communities when we travel to do research. And I feel so privileged. I feel like it's such a privilege that we had these opportunities, we had the money to go to these environments of global importance for the carbon cycle and the climate system. And so I wanted to talk a little bit about what I think that we can learn by talking to the communities when we travel there also. And so I think I spent more time on that in recent years, leading up to my new assistant professorship in Chicago. So to start this section, I just want us to think about this phenomenon, Encuentro das Aguas, which is the meeting of the waters. It happens a lot in the Amazon River Basin, where you have a very sediment-rich tributary meeting with a very sediment-poor tributary. So I think this image taken by our colleague, Chris Linder, I think it was the meeting of the soil moist river, which is very sediment rich, with the Rio Negro, which is really sediment poor. But this also happens close to where we did field work that I was showing you. This is the meeting of the Tapajos River downstream of Obidos and the Amazon main stem. And you can see from just Google Earth how different the colors of the rivers are. And then we, with Jose, who works with the community of Arapixuna, which is a Várzea, a flooded rainforest community between Santarém, or off a little bit away from Santarém, which is the city in Pará where we would often fly into. That community sits at that confluence of the two rivers. And so we visited the community, and I guess we went back in 2018. We presented to our colleagues in Santarém our Rant Oxidation results, to talk to them about what we think is going on based on those results. And then we visited Arapixuna to work with school children in the community. And we spent some time doing workshops on the topics of the science that we are studying, like why we are going to the Amazon River, to what kind of questions that we are asking there, and what kind of tools we have to look at river land dynamics in the Várzea system, the flooded rainforest system. And then we also used artistic techniques we had the students kind of depict or summarize what we learned through the week with artwork. And so we had them create this huge exhibit in the community of over 40 artworks depicting their experience and their knowledge of the Amazon and Tapajos rivers where they grew up. So here is the exhibition that we had in Arapixuna after we did the workshops with the students. And I guess, I didn't do any official research or anything, but based on these informal surveys with the students, we found that after our work with them, combining lab, field, and also artistic approaches to learn about the Várzea system, 40% more students felt that they had participated in a science experiment compared to before our activity together, our workshops. And then after our workshops, 10% more students said that they wanted to become a scientist. So I think that it was a successful way of engaging and getting the students to understand the science that we do when we come to the vicinity of where they live. And also, I think for me, and hopefully for the other scientists that I was with, it was an opportunity for us to learn more from the communities that we work in. I think it's inevitable that we have an impact on the communities when we come from outside and travel to a place to do field work. And so I think that these opportunities, and maybe through the art, there's a way for us to be better at learning from the communities too. And perhaps this learning process can drive some of our research questions going forward too. I thought the exhibition spaces were also really cool and useful for that two-way exchange of knowledge as well. We ended up printing the artworks and connecting them to another chapter of these artworks that occurred in the Fraser River Basin through our colleagues, especially my colleague Bernhard Peuker Ehrenbrink in Woods Hole Oceanographic. So we displayed these artworks at Vancouver Science World as well, so that us in Vancouver could connect our experience of rivers to people in the Amazon and how they experience rivers. And we actually, I don't know if you can see my face right now, but Bernhard helped me publish a lot of the artworks as greeting cards. And then in the back, it has a little bit information about our Global Rivers Observatory that we're all part of. And so these artworks actually really join a global student exhibition on many river systems where our colleagues work. And just from some of the comments that were left behind in the exhibition in Brazil and our exhibition in Canada, I felt, just by reading some of the comments, I felt like there was learning going on. And it was not only, it was not only the scientists driving that learning process, it was the community members being the teachers in many ways. So I'm very hopeful that going forward, it is possible to have more of these learning experiences from communities and have that be part of our research process. And that's what I've been working on in recent years. When I was a postdoc in Vancouver, I was working with a nonprofit in Inuit, Arctic Indigenous nonprofit in Nunavut, based in Nunavut, looking at how we can combine scientific data like satellite imagery of the ice surface and combine it with Inuit knowledge of environmental change and environmental risk. And we've been working together to put all these different knowledge sources on one platform so that communities can use all these different knowledge sources for climate adaptation and community-driven research, community-driven environmental policies. And then that's what I hope to continue in my newest position that I just started in Chicago. I'm spending a lot more time now teaching, but I still am working on a research program there. But yeah, a lot of my learning goals for my students are about community research partnerships and learning about rivers, but learning about rivers to connect, to figure out ways to eliminate that gap between our actions as people and the impacts that we have far downstream, like the Gulf of Mexico dead zone, and how our activities in the Mississippi rivershed could actually contribute to that dead zone, thousands of kilometers downstream. So those are some of the courses that I'm exploring and still building at the school, since it just started. Some of my colleagues do some great stuff looking at this intersection of chemistry, environmental chemistry, and art too, such as my colleague Claire over at the Art Institute. She actually visited a river basin in the Midwest and did soil chromatographies, very simple soil chromatographies on coffee filters, I think, to convey it's kind of the same thing that we often look at, which is the same things that I was talking about, which is like the landscape diversity and the molecular diversity of soils that are being mobilized in the Amazon. In some ways, I feel like she was conveying a similar thing with her soil chromatography exhibition that she was doing around this river basin. And then through my students too, so I'm not only learning from the professional artists in the school, but I do think I'm learning a lot from my art students also. So this is an example of a homework that I gave them to look at geological layers in their home. And they really expanded my understanding of the way that we can look at environmental and human history together. So they not only looked at soil layers, but they looked at how in Chicago, the newer buildings are layered over the older buildings that experienced that were decimated by the Chicago fire. And so they're really expanding my, how I look at environmental history with human history. And I really like this quote that one of my students left behind. I'll just give you a second to read it, about how reading the layers is like a code for reading time, and how it can help us slow down as people in the way that we observe different layers that exist in nature and in the environment around us. So I liked, I think that there's lots of learning opportunities that are going on at the Art Institute. And so, yeah, it just makes me feel like excited, and that we can perhaps learn a lot from artists, and that maybe art can help improve some of our approaches as researchers in the way that we design experiments, and in the way that we engage with people and the human history that is underlying a lot of the natural systems that we observe as geochemists. So that's my hypothesis. I will spend some time, many years, exploring that hypothesis about art, but I just wanted to share that here with this community, and end with just the main bullet points of what I talked about in case anyone had questions. And then I put some contact information at the bottom in case there's any reason that you would think my position at the Art Institute would be useful to you. I encourage you to, or interesting to you, I encourage you to contact me. And that's it. So I'm at 43 minutes. So.
Oh, great. Sarah, thank you so much. I appreciate so much, about your talk. It's not only a fantastic science part, the POC, but also how to transfer the knowledge to the community. I think this is a very, very important part. And I think this talk series, we need more like this kind of activity. Particularly, I guess, when we put it online, that more and more high school, community college students could be also come here, want to watch this kind of river delta environment talks. And I think this is great. We need more to, particularly, I think your work, your job is very important to give this artist and some kind of sense of environment change, climate change, like the movie star who the Leonardo DiCaprio, he talked about climate change. I think it's very important. Thank you. Okay, so we have 10 minutes before 10, and so I know a couple of people had to run. And Jim, you raise your hand. I know you have a class 10 o'clock. Go ahead to ask questions. Jim Best.
Thanks, Paul. Thanks, Sarah. Thanks ever so much. It's a fascinating talk. Yeah, I just had two questions. The first was, I noticed you get your POC flux from looking at the backscatter intensity of the ADCP, and just wondering how you did that. And the second question, I'm not a geochemist, is what was the oldest POC that you actually found? And what I'm wondering is when you think about the Amazon and the range of different age terraces, is much of the POC very, very old carbon that's coming from those really old terraces?
Yeah. So, for the first question with the ADCP, we use the ADCP primarily to reconstruct water velocities. So we didn't use backscatter at all to get particle concentration or anything like that. We just looked at it we just used the ADCP to get water velocities. And then we used some previous models for depth related sorting of sediment concentration in the Amazon to basically extrapolate our depth specific sediment concentrations into the whole cross section. And then the product of that was our sediment fluxes. Okay.
No, I was interested because it looked like the plot that you had, it looked like you had the sort of flux across the whole of the channel at Oberdos, which looked, I just think it was the way that you got that through the backscatter.
Yeah, actually, it was just an extrapolation. Yeah, we followed some of the work that has been done using this model at Obidos and the Solimois and Madeira rivers in previous expeditions. So we just kind of reconstructed the cross section just through extrapolation, just filling in the gaps. So there could perhaps be inaccuracies because we didn't measure sediments in all everywhere. So this is just based on point observations of the what's on the right, our heat map on the right.
Okay.
We didn't use the ADCP directly to get particulate organic carbon or particulate organic matter concentrations. We just used the depth specific samples and extrapolated from there.
Okay.
And then,
sorry, go ahead, sorry.
And then the second question, okay, I will admit it's been a while that I looked at the radiocarbon data, but some of the oldest pools had a fraction modern of 0.4. Someone else in the audience, can they convert that in their head? I can't remember right now how old that is in radiocarbon ages.
6,000 or 7,000 years.
Okay, I knew someone would know. Thank you. Yeah, okay. I was afraid to really be off by order of magnitude. So yeah. So that hopefully gives you an idea. There's certainly even older pools. Perhaps we think there's a very small component of petrogenic organic carbon as well, which is even older. So, but our oldest measurement is still a mixture of even older things in there, I guess I want to say.
Okay. Okay. Many thanks.
Oh, Dave.
So Dave, you have a question?
Yeah, sure. Wonderful talk, Sarah. How fun to see the ramp pyrolysis stuff applied to the nature of POC in the Amazon. It's just mind-boggling and fun. I think back of the old Hedges carbon-14 paper on the Amazon where he had the coarse fraction was very young and probably particulate leaves and stuff. And the the very fine fraction, which was probably associated with the sediment and soils, was thousands of years old. Did you do any grain size fractionation in the POC to see if there was a coarse labile fraction versus a fine soil fraction? Or density? Density might show you a similar thing where the coarse kind of leaf litter might be much less dense than the terrigenous laden soil profile carbon.
Yeah, so I do remember doing that. So we had depth profiles of bulk radiocarbon, and there wasn't much depth related differences in the radiocarbon. And so we thought that we didn't really think that there was that much difference, that much more of that, perhaps more buoyant, less dense, fresh organic matter. And you may notice that we combined all our fractions into one major fraction. We didn't do the same separation as Hedges, above and less than 63 microns in diameter. So we looked at just everything over 22 microns in diameter. So, and I did do grain size. I did do grain size analysis. I don't have that data right here. So I can't remember the differences well, in general, I guess the grain sizes were higher, deeper down in the cross section, in the deeper samples. But I will say that I do know that that is the result from the Hedges work. However, interestingly, no matter what gas fraction that we separated out, we weren't really able to get a very modern signature for organic carbon that would reflect really fresh vegetation. So that's kind of one of our big results. Because some of the gas fractions here, if you look on the left, the bar height is radiocarbon age. And that is a relatively, maybe is at most a quarter of the organic carbon that is in that sample, in that first gas fraction, in the youngest gas fraction. And yet still, it is not very close to a modern age at all. So we really think that the vegetation component is quite minor, which is a departure from the Hedges. I think it's a bit of a departure from the Hedges conclusion.
Yeah, very nice. I had a question. You kind of have equivalence between temperature of the pyrolysis and the activation energy. How would you see the trends also in, you mentioned molecular diversity, but also turnover time? Do you see trends that it might be associated with temperature? It seems like you get more complex molecularly as you get the higher temperatures. You have kind of geopolymers that would turn over more slowly. I'm just wondering, as you see, you've taken the jump to turn it into activation energy. I'm wondering if you're willing to take a jump and put in some idea of trends in molecular diversity or trends in microbial carbon turnover time.
So I guess to me, I'm not ready to make that jump with molecular diversity, because what would be ideal though is if I could get a thermogram. Okay, so what I started thinking of thermograms, especially with my colleague Jordan Hemingway, we started thinking of thermograms as the narrower they are, the less molecular diversity there is. So I can't really say that for the higher activation energy pools. I would like to see if I could make those pools a separate thermogram in itself as well. I think that would answer the question. So I'm not ready. I wouldn't make that jump yet. You know, I don't know if I can link the higher activation energy pools to something about their intrinsic molecular diversity. But turnover time, I mean, I guess I would, what I'm seeing happening in the Amazon, or how I conceptualize it, is there is mixing of different soil organic matter pools that have their own turnover times in the terrestrial biosphere. The older stuff, it's older, so its turnover time is longer. And the younger stuff, the younger soils, they're younger, their turnover time is faster. So you have a mix of soils that are turning over at many different rates. So yeah, I guess the activation energies would be, the higher activation energy would reflect slower turnover times in the terrestrial pool. In the river pool, we're not sure. We'll have to compare with, I think, a lot of the work that Brenna, Kirsten, Brad, and Valier are doing in the mud banks in the coming years, hopefully this summer.
Okay, cool.
Great,
Hey,
thank you.
Hey, Bob.
Yes, I'll join in and say that was a really nice talk, and I totally agree that this interaction between researchers and the people in the areas that they're carrying out research, the communication in both directions is incredibly important and one of the most enjoyable aspects of doing research. So I thank you for really emphasizing that component. My science question is specifically concerns the thermograms, and it's along the lines that Dave was just asking you about, but I'm interested in how do the mineral organic matter associations, how do those, if at all, influence the activation energy calculations that you make?
That is a good question. Let me think about that, because well, Jordan Hemingway's my colleague's most recent paper connecting molecular diversity activation energy was somewhat about that. And I hope not to say it in the opposite direction, but mineral preservation, I guess you would expect that mineral preservation, okay, I don't know if this will answer your question, but mineral preservation, the idea is that it maybe would promote diversifying of organic matter. Yeah, I guess it would lead to greater diversity of organic matter through time if there's mineral protection as that organic matter ages. And so I think it's interesting in the Amazon, it's pretty old, the soil organic matter, but the thermograms are, relatively speaking, not very molecularly diverse compared to other thermograms that you get, especially thermograms in other river systems. And so this is really perhaps the argument here that we're making is that the narrowing of this thermogram in the Amazon really perhaps reflects selective preservation rather than mineral protection of Amazon POC, because the molecular diversity is, relatively speaking, relative to other thermograms, is not very high. If we make that jump from thermogram, the overall thermogram shape, to molecular diversity. I don't know if that answered your question super well.
Well, to just give an example, I was particularly interested in whether an association with a montmorillonite, for instance, might give you a different thermogram than an association with kaolinite, something along those lines.
Yeah, I didn't explore. That's a very good question. And I know that there's other people trying to answer that, looking at how thermogram shape is driven by the presence of minerals that can protect the organic matter. I didn't really think about that much in this project though, but I feel like I should have. So thank you for the suggestion.
Okay, thank you. Thank you.
Is there anybody, any question? Sarah, you look like in a PhD defense. You know, the people, David Master, Bob Eller, Jim Best, they are one of the best expert in the world to study Amazon carbon, you know, Amazon system. Okay, here's a little bit easy question. And so we all know the last couple of years, Amazon River Basin experienced a tremendous, huge of the fire, destroy the rainforest, and even the farmer deforestation. They put so much fertilizer on the land. So how this will affect, burning is one thing. There could be some old carbon, new carbon, going into the river. And fertilizing definitely will boost the primary production, both in the river and the coastal environment. How this will affect that kind of organic carbon signal in both the estuary and the nearshore environment?
Yeah, I think that's a very good question. Well, you're making me wonder how we would see the impact of black carbon and maybe autochthonous production in thermograms, which is an interesting question, whether we can somehow tease out that signal with the Rant oxidation technique. So that's cool. Yeah, I guess the paradigm is that black carbon, for example, you would think that it's recalcitrant in the environment. And so that would affect the burial of that organic carbon and its persistence in the mud banks. But I know that that's being revisited now in recent years, whether black carbon is in the ocean is truly marine or terrestrial derived. And so, but the paradigm has been that black carbon is recalcitrant to organic matter degradation. So you would expect more burial of that in the mud banks. And then fertilizer, that's very interesting. I didn't think about that much, but I guess if you expect, like in the Mississippi rivershed, more fertilizer and more organic carbon production, you would think that that's in the marine system that would be more labile because it's fresher organic matter being produced.
I hope Valley, this coming summer, if he can really go there, hopefully with the new sampling, maybe have some interesting finding, about this the signal. Okay, I know is people has already begun to leave. And any other question? If not, thank you, Sarah, so much. Sarah, I'm sorry, could you back to your, could you back to your first slide? Because I missed the recording the first couple minutes of your talk. I want to at least keep a record. Maybe I'll try to do something later to make that part, but I want to in the beginning, at least, can move down from a little bit. Right. Yeah, something information is archive, so that's great. That's great. Thank you so much.
Thank you for the opportunity, and nice meeting people that I have never spoken to before. So nice meeting you all.
Yeah. So Sarah, maybe we can talk about, because like the Mekong system, the Irrawaddy system, we need that kind of a social connection component in our future research. And if you have that kind of experience, maybe we can talk a little bit, over the Myanmar, in Vietnam, even in Ganges. That's just, we really need that kind of, extension.
Yeah, I would love to help. I'm spending more time these days, I think, on that. So I would love to help you if I can. Yeah, we can talk. Thank you.
That's very good. Okay, cool. Thank you, Dave. Thank you, Bob. And
sure, good to see you. Thanks, Sarah.
Have a good weekend.
Sarah, what journal is the Jordan Hemingway 2019 paper in?
Nature.
It's in Nature. Okay, so I missed the big one. Sorry. Thank you.
Called Selective Preservation of Organic. Jordan Hemingway. You should find it. Nature.
Yeah. Sarah, how about you just drop Dave an email? You see Demaster at NCSU.
I can get it. I'm good. I'm good.
Okay.
You're retired. You don't need to read other people.
Mhm. Yeah, you'll find it interesting. And thank you for your questions. It was nice meeting you also in person. So. Okay.
Okay, cool.
Bye.
Thank you. Thank you.